In traditional software architecture, determinism is the foundational bedrock. Whether building a compiler or a relational database, an identical input guarantees an identical output. When interacting with large language models, developers naturally expect this same reliability. The standard method for enforcing it is setting the inference temperature to 0. This curve visualizes the probability distribution of token predictions. At exactly 0, the distribution sharpens infinitely, defaulting to an argmax function. On paper, this strict algorithmic constraint strips away all stochastic variance, mathematically mandating the token with the highest predicted log probability. When we move this theory into the real world, the math begins to drift. Researchers testing major reasoning benchmarks like MMLU, tasks requiring consistent logic to achieve a high score, found that even with deterministic settings locked in, identical runs produced accuracy variations as high as 15%. Submitting the exact same prompt to the exact same model yields divergent results, because LLM inference in a production environment is inherently non-deterministic. The root cause lies entirely outside the language model's probabilistic algorithms. It is a physical consequence of executing operations on high-performance GPUs. Before analyzing the hardware execution, we must rule out upstream API translation errors. Developers integrating Amazon Bedrock recently exposed a pervasive software bug involving how the integer 0 is handled. Because 0 evaluates as falsy in Python, the software inadvertently dropped the parameter from the payload, forcing the inference engine to fall back to a default, highly stochastic temperature of 0.75. However, patching these integration bugs only exposes a deeper structural issue. Even when the temperature payload is perfectly transmitted and the argmax function is strictly enforced by the engine, the output remains physically unstable. Diagnostic studies measuring token-level probabilities demonstrate that this hardware-induced instability does not manifest uniformly. When a model is highly confident, with a token probability approaching 1.0, or highly unconfident, near 0.0, the predictions remain perfectly stable. This spectrum illustrates exactly where the variance strikes. The extreme ends are secure, but the middle zone, where token probabilities hover between 0.10 and 0.90, operates as a highly volatile vulnerability space. If the top two candidate tokens possess nearly identical probabilities, for example 49.5101% versus 49.5100%, ambient microscopic fluctuations in the hardware execution easily invert their rankings. The autoregressive nature of the transformer then feeds this newly selected token back into the context window for the next step. A microscopic deviation cascades into a completely divergent logical trajectory for the remainder of the generation. The origin of these microscopic probability inversions begins at the level of computer arithmetic. Executing floating-point operations on parallel GPUs breaks the mathematical law of associativity, meaning the specific sequence in which numbers are grouped physically changes the result. This variance is severely amplified by the industry's reliance on low-precision numerical formats, specifically bfloat16, which is utilized heavily to maximize memory bandwidth and computational throughput. This visualizes a bfloat16 number, which leaves a highly restricted 7-bit block for the mantissa. When a GPU adds two floating-point numbers of vastly different scales, it physically aligns their decimal points. The smaller number shifts, pushing its least significant bits completely outside the 7-bit boundary. These overflowing digits are permanently lost to rounding. Because of this strict truncation, the exact sequence of the addition physically changes the final mathematical sum. A single LLM forward pass requires executing billions of these matrix multiplications simultaneously across thousands of parallel streaming multiprocessors. We can visualize this massive parallel accumulation through a physical system pouring exactly 10 kilograms of sand using 1,000 separate funnels simultaneously. While the absolute total mass remains exactly 10 kilograms, the microscopic arrangement of the individual grains, how they stack upon one another, and the precise shape of the resulting mound is completely unique every single time the action is performed. In deep learning math, this arrangement of grains represents the exact shifting sequence of floating-point additions occurring across the GPU threads. The ambient rounding differences accumulating at the margins of these sequential additions slightly alter the final logic weights. This microscopic numerical noise is precisely what flips the ranking of closely matched tokens. If floating point non-associativity explains how the math changes based on execution order, we must ask why a static, identical prompt executes in a different sequence from run to run. The answer lies in continuous batching. To operate profitably, cloud-based inference engines dynamically bundle disparate inbound requests from multiple users into a single computational batch. Because global server traffic fluctuates by the millisecond, the exact size and shape of the batch that a specific user's prompt is grouped into is completely random from the perspective of that user. The hardware execution fails to maintain determinism here because the highly optimized CUDA and Triton compute kernels powering these models lack batch invariance. This grid represents a computational kernel. Processing a batch of 4 utilizes large quadrants, but scaling up to a batch of 128, the kernel shatters into a complex interlocking tile grid. As this parallelization strategy physically shifts, the exact sequence of floating point accumulation shifts right along with it. Consider your daily commute on a highway system. Your starting point, the prompt, and your intended destination remain identical every single day. Despite having a fixed route, your exact driving speed, the specific lane changes you make, and the exact moments you hit the brakes are dictated by ambient traffic. Because an individual API user cannot control ambient server volume, their logically isolated prompt is continually subjected to fluctuating, traffic-dictated mathematical sequences. As models scale to hundreds of billions of parameters, they exceed the memory capacity of a single machine and must be physically sharded across interconnected GPU clusters. This physical distribution introduces tensor parallelism. During a forward pass, partial mathematical results computed on individual GPUs must be synchronized and summed together via network operations known as all-reduce. Varying the tensor parallel size, such as choosing to serve a model across 4 GPUs versus 8, alters the arithmetic reduction topology. It dictates a different number of partial sums that must be aggregated across the network. Due to the laws of floating point non-associativity, aggregating 8 smaller partial sums from a larger cluster yields a mathematically divergent final logit compared to aggregating 4 larger partial sums. This infrastructural instability is profoundly magnified in mixture of experts architectures, which decouple parameter count from active compute by utilizing a hard-step router network to dispatch individual tokens. Think of this mechanism like a hospital triage system. A microscopic variance in a patient's vital score can route them to an entirely different specialist ward for treatment. In a mixture of experts model, a tiny decimal fluctuation in the router's probability score triggers a mechanical switch, instantly diverting the token to a completely different sparse subnetwork containing billions of distinct parameters. This router variance is exacerbated by expert capacity limits, which forcefully drop or reroute overflow tokens when massive spikes in ambient server traffic overload a single expert. Distributed infrastructure scales microscopic decimal truncation into divergent semantic results. This numerical noise is what causes advanced alignment algorithms to chase phantom gradients, explaining why reinforcement learning pipelines often collapse into generating nonsensical, looping text. The persistence of non-determinism in commercial LLM deployment is not an accident of oversight. It is a highly calculated engineering compromise optimized to maximize tensor core throughput and minimize latency. Forcing a language model to behave deterministically isn't a matter of writing a cleverer algorithm. It requires deliberately sacrificing the system's speed, scale, and operational efficiency. Operating on a dedicated personal GPU lets an engineer eliminate that ambient server noise by enforcing a strict hardware batch size of exactly 1. Moving down into the software layer itself presents a second choice, relying on auto-tuned speed or shackling the system to hard-coded determinism. Standard NVIDIA libraries like QBLAS and QDNN default to auto-tuning. At runtime, they automatically hunt for the absolute quickest mathematical kernels available. Picking different fast kernels on different runs destroys any chance of reproducing the same output. The only solution is to explicitly override the system's environment variables before the operations even launch. Modern AI attention is chaotic by design, unless a developer mathematically shackles the process.